This lesson is part 1 of section 2.1 on tangent lines and rates of change. We have two objectives for today. We're going to determine the slope of a function at a value of x, and we're also going to find the equation of a tangent line to the graph of a function at a given value of x. Now, before we begin, I want to make sure we go over some vocabulary from geometry. So if you'll recall, a secant is a line that will intersect a circle at 2 points, while a tangent is a line that touches a circle only at 1 point. Now, if we kind of generalize this concept to functions, a tangent is a line that will touch your function but not pass through it. So given the graph of this function here and several lines that intersect this function, which of these lines would be considered tangent to your function? So we're looking for lines that are going to intersect the graph of this function exactly once, but they won't pass through the function. So we want it to just touch, but not pass through our function. So if we look at this first line here, here is a tangent line because it intersects exactly once, but it does not pass through the function. Same thing with this second line here, okay? But this third line fails that. This is not a tangent line because it passes through your function. Okay, so now we're back to our note sheet. What we're going to do now is actually define the slope of a secant line. So remember, a secant line is a line that passes through the graph of a function twice. Okay, so here we've got the graph of some function f. Now on this graph, we have a point that lies on the graph of that function, x comma f of x. So it's just some arbitrary point here. Now I want to consider another point that lies on the graph of this function whose x-coordinate is h units away from x. In other words, I'm adding h to this x to come up to another point that lies on the graph of this function here. Okay, and its x-coordinate would be x plus h, while its y value here, the y output, would be f of x plus h. Now, if I connect those 2 points, what I create here is a secant line. Okay, not very straight line, but whatever. And if we want to consider the slope of that line, remember a slope is just found, or the slope of a line is just found by taking the change in the y values over the change in the x values. So in this case, if we are going to find the slope of this secant line here, the change in my y's, that's going to be found by taking f of x plus h, this is the y value here, minus f of x. Okay, and then I'll take the difference of the x values here. So that's x plus h minus x. Okay, now if I simplify in the denominator here, those x's will cancel. And I'm left with f of x plus h minus f of x over h. So you probably recognize this. Remember, this is the difference quotient. We studied that in first semester. And we also just did that in our day 1 of pre-calc review as well. So this is an important concept here that we're going to use throughout. Okay, so now that we have the slope here of a secant line, I want to go through some terminology with you. So the slope of a secant line obviously is referred to as the difference quotient, as I mentioned before, but we also refer to it as the average rate of change of a function over a certain interval. Now we also studied the average rate of change in first semester, and it was actually during the same exact section that we learned about the difference quotient. I believe it was section 3.3 if you're curious. So basically these are two ways of saying the exact same thing. You're finding the slope of a secant line. Now our goal is to actually use the slope of a secant line in some application problems. We're going to calculate the average velocity for a position function over a certain interval. So that's kind of what we're going to get into tomorrow, is the application of these concepts today. Okay, our next topic of discussion is the slope of a tangent line, but what we're going to do first is actually consider a secant line. So I'm going to draw a line through points P and Q. Okay, now, so let's say I decide to move that point Q, and I want to move it so that it's a little bit closer to point P. So if I were to do that, let's say it's slightly closer to point P. Now, remember before, let's say that that x value here is x plus h. So it's h units away from x right now, this distance here. But if I move that closer, now it's slightly less than x plus h, right? Here, that new x value here is slightly less than that. But let's just draw in that secant real quick. All right, but let's say I'm not really happy with that and I want to move even closer to P. And I keep doing that. I move closer and closer. Okay. Notice that my x coordinate here gets that value here, x plus h, moves in, which means the h is decreasing. So if I keep going and keep going and keep trying to make this point closer and closer and closer, well, what ends up happening is that I end up with a tangent line. So I keep moving this point Q closer to P, and meanwhile this H value here keeps decreasing. In other words, it gets closer and closer to 0. So to help illustrate this, here I found an applet online, and I know this moves pretty quick, but basically what you're seeing is a green line that represents a secant to the graph at the point 113. Okay, so here we've got a secant, and point Q is the other point that intersects that graph, this function in red. Okay, now the blue line is your tangent line, so it's the tangent line to the function at the point 113. Now to find the slope of this blue line, right, we don't have a second point that lies on the graph because it's not supposed to touch the graph at 2 points. It's only supposed to intersect exactly once. But what we can do is approximate that actual slope of the tangent line by bringing that point Q closer and closer and closer to point P. So if we look at the graph and we look at the slope of our secant line, as we get closer to point P, your slope turns into the slope of the tangent line. So that's what we're going to be doing in this section. We're going to be finding the slope of a tangent line using the idea of the slope for the secant line. Okay, so now if we want to talk about the slope of our tangent line, that means that we're going to use the slope of the secant line as an approximation. And to get a more accurate approximation, remember, we want to move that point closer and closer and closer to point P, which means that your H value, okay, has to be getting closer and closer to 0. Whoops, that says loser. There's supposed to be a C. Sorry about the typo. But anyway, if we're looking at the slope of our secant line, remember that's f of x plus h minus f of x over h. We're trying to find that slope and use it as an approximation by making h closer and closer to 0. In other words, we're going to find the limit as h approaches 0. Now this gives us the slope of the tangent line. Okay. Now above you can see it says that we're finding the slope of our curve f of x. So this is saying the slope of our function at some arbitrary point. Now that's kind of a weird concept here because we're saying that if we find the limit as h approaches 0 of this difference quotient here, that we'll find the slope of our tangent line. And now above it says that this is actually the slope of your curve f of x at some arbitrary point. Now the reason why these two things are really one and the same is because if I kind of zoom in here, okay, this is a tangent line, and as I zoom in really, really, really close to that specific point here, I don't know why it's not letting me zoom anymore. Oh, there we go. Okay, so see how the slope of that tangent line and your curve pretty much start becoming indistinguishable. You can't really tell where the blue and the red line, you know, aren't overlapping. And if I make this even closer and closer and closer, and I get really, really zoomed in here, that line of the tangent, okay, the tangent line and the actual function f of x here become one and the same. So that's why we can say that the slope of your tangent line is the slope of your function f of x at that specific point. All right, so here's some of the terminology I was just sort of alluding to. We can say that the slope of your function at x equals a, so the slope of your function at some arbitrary point, is the same thing as the slope of your tangent line to your function at some arbitrary point. In other words, if you find the limit as x, oops, okay, this is a really bad thing. If I write x approaches 0, when you find and evaluate your limit here, you're going to get really confused. So the fact that I just said that out loud, I hope doesn't make it worse for you, but it's supposed to be the limit as h approaches 0. This is really important. Don't ever write x. So the limit as h approaches 0 of your difference quotient, f of x plus h minus f of x over h. So this limit, after you evaluate this, you can say that it's either the slope of your function at that specific value or the slope of your tangent line to your function at that specific point. And we'll definitely get into some application problems, okay? We're going to talk about the instantaneous rate of change and the instantaneous velocity in our next lesson. Okay, let's start with some example problems. In number 1, we're supposed to find the slope of our function. Okay, so the slope of a function at a specific value x equals a. So to find this slope, remember we want to evaluate the limit as h approaches 0 of your difference quotient. So f of x plus h minus f of x over h. Now in this case, since x is equal to a here, I'm going to replace this x with an a and this x over here with an a as well. So I have f of a plus h minus f of a over h. All right, now I'm going to input let's do this in different colors. Okay, I'm going to do this portion here, f of a plus h in red, and then I'll do f of a in, oh, that did not change colors, sorry. I'll do that one in orange. Okay. All right, so if I'm going to evaluate f of a plus h, that means I am substituting a plus h here into the function. So that means I'm taking the limit as h approaches 0 of x, a plus h squared, because again, I'm inputting this into that function here, plus 2 times a plus h. So that's the first part. Now for the second portion, which I'll do in orange, now I'm going to subtract f of a. So here make sure that you do put parentheses around f of a, because a lot of you have a tendency to forget to distribute that negative that should be distributed to all of the terms here for f of a. So f of a, if I evaluate, I'm just plugging in a into the function, and I end up with a squared plus 2a. Now all of that is being divided by h. So now I'll just work on the algebra part here of simplifying this. So now we're taking the limit as h approaches 0, and I'm going to keep writing this out there because it's not equivalent if you forget to write in the limit as h approaches 0. So, it's nitpicky, but please make sure you do write that in. But we have a squared plus 2ah plus h squared plus 2a plus 2h, and then minus a squared minus 2a, all over h. All right, now we can cancel out some of these terms. The a squareds here will cancel, and that 2a will also cancel with that negative 2a. And then if I look at all of my leftover terms here, each of these in the numerator has an h, so I can cancel and factor here, I can factor and cancel out the h in the denominator, so I'm left with the limit as h approaches 0 of 2a plus h plus 2. Now, to evaluate this limit, remember, algebraically, you can always just substitute that value into your function here to see what you would end up with. And if I do that, I end up with 2a plus 2. So the limit as h approaches 0 of my difference quotient is 2a plus 2. In other words, this is the slope of your function. Let's call it f of x. Okay, this is the slope of your function at any x value, at any x equaling a. Okay, now in part B, we're asked to write the equation of the tangent line at x equals 2. So notice here we're finding an equation and not just the slope of our tangent line. So to write a linear equation, you need two things. You need a slope, and you also need at least a point, and sometimes they even ask you for it in slope-intercept form, so we might need a y-intercept. So both of these things are actually pretty easy to find because we already know what point our tangent line is supposed to intersect our function. It's supposed to intersect when x is equal to 2. All that we have left to figure out is what the y output would be. So we want to find f of 2. We want to know exactly where our tangent line is intersecting our function. So I'm going to plug in 2 into my function. So I'm evaluating 2 squared plus 2x. So I end up with 2 squared plus 2 times 2. So I end up with 8. So the point 2, 8 lies on the graph of our function, and it's also where our tangent line intersects our function. Now for the slope, we know that the slope of our tangent line, okay, is the same as the slope of your function at any value. So here we found an arbitrary slope, 2a plus 2. So in this case, since x is equal to 2, I'm going to plug in 2 in for here. It's just another way of saying let x be any value a, right? And now we have a value for a. A is 2. So here the slope, if I calculate, okay, is going to be 2 times 2 plus 2, 6. So now I have a slope and I have a point, and I'll just put that into point slope form. So I have y minus 8 is equal to 6 times x minus 2. So in other words, if I just put this into slope-intercept form, I have 6x minus 4. All right, so this, either one of these are fine for your final answer, but this is the equation of the tangent line at x equals 2 to the function here, x squared plus 2x. Okay, question 2a is pretty similar to question 1a. I just want to get some more practice, and this is a little bit different looking function as well, so it's a little bit different with the algebra here. But we want to find the slope of a function at a specific value of x, in this case at a. Okay, so we want to take the limit as h approaches 0 of our difference quotient. So I'm just going to write that difference quotient like we normally would, and then I will evaluate it when x is equal to a. So I have f of x plus h minus f of x over h. And since I'm letting a equal x, or x equal a, we'll take the limit as h approaches 0 of f of a plus h minus f of a over h. All right, so now all we have left to do is make some appropriate substitutions. We have f of x is equal to 1 over x. Okay, so that means f of a plus h, remember we're going to do, let's do this in blue. Remember, we're going to substitute a plus h in for x. Okay, so the algebra here is important. Make sure you can input that into the function correctly because you'll have 1 over a plus h. Now, let's do it in orange. Let's take f of a. So we're subtracting f of a, and so I'm going to plug in a into the function, and I just get 1 over a. Now, don't forget to divide by h. Okay, so I'm finding the limit as h approaches 0 here of this expression. So now we work on simplifying. So here the algebra is a little bit different. You can approach this a couple different ways. You can find, a common denominator here in the numerator and then divide by h. But I think it's probably easier just to get rid of the fraction in general. I'm going to multiply by a times a plus h over a times a plus h. Okay, so now that numerator here, let's write this above here. I'm going to copy everything down. So the numerator here becomes a minus a plus h. Okay, after I distribute this to each term here, I'll be left with a minus a plus h. Ooh, gosh, I almost made a bad mistake there. Make sure you put parentheses around that a plus h again because you're subtracting an entire expression here. So you'll have to distribute that negative. I almost forgot to do that. Now in the denominator you have h times a plus h. Okay, so if we simplify the numerator even further, those a's will cancel and I'm left with negative h over h times a plus h. Here I can cancel the like factors, h and h here. So I have the limit as h approaches 0 of negative 1 over a times a plus h. Okay, so let's evaluate this limit. The limit as h approaches 0, remember you can just plug in 0 here. You end up with negative 1 over a squared. So this is the slope, okay, of, what did we call this, f of x? Okay, so this is the slope of f of x at x equals a. Okay, here in question B, it asks, where does the tangent line have a slope of negative 1/4? In other words, at what point, okay, will a line that is tangent to the graph have a slope of negative 1/4? So this question really relies on us piggybacking off of our last answer and understanding this really important concept. I know I've said it a couple times already, but the slope of your function, okay, is the same as the slope of your tangent line. So this is for any arbitrary value of x, right? We have a slope of negative 1 over a squared for our function. So let's take negative 1 over a squared and we'll set it equal to the slope of our tangent line because they are supposed to be one and the same. If we want to find exactly at what point, we need to find the specific value of a. In other words, here a squared is equal to 4. In that case, a can be positive or negative 2. So if I were to graphically show you this, you have some function here, 1 over x, so we've got, this is kind of the graph of that function. At x equals 2 and at negative 2, we have two lines that are tangent to the graph at those specific x values. And in both cases here, you can see the tangent line would have a negative slope of negative 1/4. So my sketch was kind of crappy because it should have been like here, I guess, at negative 2, x equals negative 2. A little bit of a less steep slope. That looks more like negative 1/4. But anyhow, I hope you get the point. But basically, now all that we have left to do is figure out the exact y outputs for x equaling positive 2 or negative 2. So we have the point 2 comma 1 over 2 and the point negative 2 negative 1 over 2 just by plugging those values back into your function. So here at these 2 points you would end up with a tangent line that would intersect the graph of your function, and that slope for that tangent line would be negative 1/4. So these are the two different answers for part B. All right, Deuterinos, that's the end of the lesson. Just make sure that you're comfortable with evaluating a difference quotient and finding the limit of that difference quotient. So there's a lot of algebra involved and lots of areas where you could make potential mistakes. So just try to be really meticulous when doing them and make sure you understand in general the ideas that have been presented in this lesson because they are the foundation now for the rest of Chapter 2. Anyhow, nice job. I will see you guys in class tomorrow.